presentation is on recent results on RSA and factorization. So it will be a little bit technical, but it is not after lunch session, so I hope it will continue. So what is the background? Famous US Shamil and Lehman. So the name. So they have actually provided a new direction in the area of cryptology. So in a secure communication, you need to have a secret key. Now, in symmetric communication, both the parties need to sit together to decide on a specific secret key. Now, it is quite hard that one person from New York and another from Paris will sit together on a tea table and toss a coin 128 times to generate the secret key. So, given that, what we need is some method where both the persons need not sit together, but over a common insecure channel that is accessible by anybody, they will be able to manage a system so that they can communicate securely. So now let us get into technical details. So for RSA, we need to generate the keys. Now we need very large primes. So with the current technology, it seems to be safe to have 512-bit primes. So that means if you write in decimal format, it will be something like a little more than 160 digits. Those kinds of primes, P and Q, and we need to multiply them. Now the first question is, how can we get large primes? So famous prime number theorem, it tells that among n integers, if you go through continuously, you will get around n by log n many primes. So that means if you randomly try for around log n many integers in a range, then out of them it is expected that one will be a prime number. So you know that the density of prime is quite good, because even if n is very large, a large number, log n is actually the number of bits in the integer. So 512 bits means you need to try 512 times, or maybe say 1024 times. So say 2000 times, that is also very fast. You can find out the prime. Now the question is, among the numbers you have chosen, how can you check which of them are prime? It is another interesting question. So there are probabilistic polynomial time algorithm, one by Solovay-Strassen and another by Rabin-Miller, through which, given an integer, you can check with a very high probability. You can tell with a very high confidence that it is indeed a prime number. So that means, say, you run the algorithm say 200 times and then say, okay, with probability 1 minus 2 to the power minus 200, this integer is a prime. So that suffices. And in 2000, there is a famous deterministic polynomial time algorithm by Monindra Agarwal, Koyal and Saxena, his students. So they could prove that actually primes is in P. So here primes is the problem prime. So you can actually, in a deterministic polynomial time, you can check an integer. But even that is a deterministic polynomial time algorithm, the efficiency of that algorithm is not pretty good yet to be used in practice. So in general, for practical purposes, to check whether an integer is prime or not, what we do, we use the probabilistic polynomial time algorithm. So a school book kind of problem is, consider that somehow you have chosen two integers and thought those are primes, but those are not actually primes, then what will happen to RSA? You can take that as an exercise. Then you need to calculate phi n. Phi is the famous Euler's function. So phi n in this case is p minus 1 into q minus 1. And then you need to find out an integer e such that GCD of e and phi n equal to 1. Again, it is very easy to find. You choose random e's, and with very high probability, out of them some of those integers will be co-prime to phi n. And checking GCD is again a very nice algorithm, Euler's algorithm, through which you can check that whether the GCD of two integers, you can do it very efficiently. And then you need to find out inverse. So D is E inverse mod phi n. That means you need to find out a D such that E into D minus 1 will be divisible by phi n. Again, that can be done very easily by using extended Euclidean algorithm. Okay, so the ideal one is Euclidean algorithm for calculating GCD. I told you Euclidean algorithm. Now publish n and e and keep n comma d private. So what you do, you just keep your d secret with you and publish n comma e to everybody. Now anybody who likes to send you some secret data, what he will do? He or she will take the message m. Message m can be thought of a bit stream. So if you can make it in different parts, you can consider each part as an integer and you calculate m to the power e modulo n. Again, you have first square and multiply algorithm through which you can calculate m to the power e mod n quite easily. So all the steps written here are very efficient. So the key generation is very efficient and encryption is also very efficient. Now the decryption is c to the power d mod n. So if you know d, then you can easily find out m. But the problem is when you do not know d, then what will happen? Now first look at the encryption function. C equal to m to the power e mod n. Anybody in the world knows knows e because that is the public encryption exponent, knows n, that is the part of the public key, and at the same time c is the ciphertext is communicated through a public channel. So c is also known. Now given that, what you do not know is m only. So in an equation you have c, e and n, everything known to you, you only do not know m. So it may seem like that it is possible to find out m, but this is known as famous RSA problem and you cannot actually do that efficiently. If you can do that, then RSA will be broken. And so this is the decryption method. So if you know d, it is very easy. If you do not know d, then you are in trouble to decrypt. So efficient decryption methods are also available, which are known as CRT RSA. CRT stands for Chinese Remainder Theorem. And here from D we calculate DP and DQ, and that helps us in the decryption process. It becomes more efficient. So security of the scheme, as I have already told, the RSA problem is given RSA public key NE and C, compute M. Now it is easy to prove that if you can factor n equal to PQ, then you can easily solve the RSA problem. Because if you know PQ, you know E, you know phi n, you can easily find out D, so you can easily find out M. So all this process is easy. So this is the scenario. So once D is known, you can get C from M. But we really do not know how D will be known. So what is not solved yet, that if one can solve the RSA problem, then can you factor in? So consider the scenario that you have C, E and N, and somehow you have an oracle or a black box where if you put C, E and N, you can immediately get back M. Now can you use that oracle to find out the factors of N? That is an interesting question. So not solved yet. Now if you can factor N is known, then everything will be broken. So what is the current scenario? So this is the data. I am not going into this, but you can see that the sizes of the integers n, which are products of two primes, there are a lot of challenge n's which people try to factorize. So this is the scenario. Until 2005 it was RSA 200, which is 200 digit integer. That means each prime are around 100 digit. That means around 300 something bits, 320-30 bits. And this is the state of the art result. So this concluded in 2009 by several researchers. So it is done by some kind of informal consortium. It started in 2007, and you can see with around 80 or more computers with different kinds of complicated algorithms in the area of number theory and computer science. So they could ultimately prove that 768-bit numbers can be factorized. So the best factoring algorithms, so those are still sub-exponential. Now trial division, if you try to factor one integer, what you have to do, if you know that it is of the form n equal to p into q and p and q are of the same order, then what you have to do, in using school book methods, you have to try all the numbers up to root n. One of them must be a factor. But that algorithm, is quite inefficient. The better algorithms are sub-exponential factorization algorithms. So one is quadratic sieve, another is number field sieve. There is also elliptic curve factorization method, but that works very well when one of the prime factors is small But for RSA, generally both the prime factors are equal. So the elliptic curve factorization method doesn't work well. So you can get this data. So 2 to the power 1024 size of n, that means n is 1024 bit integer, and in such a case the primes are of 512 bits. In that case, the base complexity is 2 to the power 86.6 around. So it is still infeasible with all the computers in the world. Now, when somebody is using RSA, the situation is not this simple, because in field, these are the parameters that you need to store in your computer. If you want to decrypt, then you need to store the private key in your computer, otherwise you cannot decrypt. So what you store in your computer, the PKCA standard, the standard tells that you need to store public parameters, NE, you need to store RSA times PQ, the RSA decryption exponent D, the CRT RSA decryption exponent GPDQ, and CRT RSA parameters Q inverse mod D. So, given all these things, if those are stored if you are writing a C program, then you are writing them as the elements inside a structure, and you are storing that structure in your machine. And when you are keep storing it in your machine, you cannot always consider that this machine is absolutely secure. It is not. There are several situations where there may be certain problems with this machine. And even without the problem with machines, there are some mathematical issues through which RSA can become insecure. So what I am planning is to cover those things. I will skip the mathematical issues. So if any of them fall into wrong hands, then there could be trouble. Now what are those troubles? So N and E, no, this is the public key. So you cannot factorize N by knowing that, but there are certain issues. If E is very small, so during encryption, what you really need, you need M to the power E mod n. And if you look at the square and multiply algorithm, if the size of E is very small, then you can do the encryption very efficiently. But you shouldn't be tempted. If you take too small, a value like 3, then there are attacks on RSA. So you cannot take very small E. If you take E of the order of 2 to the power 16 plus 1. Why 2 to the power 16 plus 1? If you think of 2 to the power 16 plus 1 as a binary pattern, you will find there are only 2 ones in the binary pattern. In the square and multiply algorithm, you need to square in each step, and you only need to multiply if you have a bit 1 there. So in the value 2 to the power 16 plus 1, you have only 2 ones. So you need 17 squares or 16 squares and only 2 multiplications. So that makes things easy for the time of encryption. Now, if you take a small e, though there is no attack yet, and most of the people use small e, upper half of d is already known. So, inside the community, this information is there, but most of the people who are not exactly in the field of this area of research, it is not known to them. That means you are publishing any, and if E is small, and what it is used in most of the actual applications, you must be aware that half of your secret key, that means the most significant bits of the upper half of D, are known to everyone. So if there is any bad implementation, such that some other part of D could be known, then you are in trouble. Now, if D is known, then you know that RSA is attacked. But consider D is unknown, but small. Why you will choose D small? Because you may think that, okay, whatever be the size of E, I give the load to the person who is encrypting the text and sending it to me. What I want, I will make my decryption exponent very small, so that my exponentiation will take less cost. So, from that point of view, you can make your D small. But if you make your D small, it was proved by Weber in 1990 that RSA can be completely attacked. And I'll try to give you the basic idea of the attack. And later Bonet and Darcy, with much more complicated lattice-based technique, shown that if D is less than n to the power 0.292, then it can be attacked. In fact, we have also tried some experiments, and with some amount of search, we could show that in to the power 0.3. That means if you are considering primes of the order of 512 bits, then n is of the order of 1024 bits, and then D comes to be around 300 bits, and that is very easy. So if you use 300 bit D, then we can break the system immediately. So, and two theoretical results, which are probabilistic factorization of n is known when d is known, and recently there is a result that if d is known, deterministic factorization of RSA is also done. So, those are two theoretical results in terms of complexity theory. And partially known cases, if E is small, as we have already told, upper half is already known. And now, in the lower half of data, if around 25% of the bits is known, then factorization can be done very easily. And if E is not so small, then the size of data you need to know varies. So you should be very careful while choosing the E. But again, current state of the art applications, they use small e, and that means everybody knows upper half of your secret key. So what is Wiener setup? You need to know about continued fractions. And again, it is very easy, school level mathematics. You can write a by b as q1 plus in this form. So you can write 34 by 99 as 0 plus 1 by 99 by 34 equal to 0 plus in this manner. So very easy to write. This is known as continued fraction. And one interesting thing is, if you take a subsequence of the expression, that is, the continued fraction is 0 to 1, 10, 3. If you take 0 to 1 and prepare the rational number, you will find it is 1/3, which is very close to 34 by 99. Because 34 by 99 is nothing but 1/3 is nothing but 33 by 99. So there is a famous theorem, quite old, as you can see, that if there are two rational numbers, a by b and x by y, such that their difference is less than 1 by 2y square, then x by y is one of the convergence of the continued fraction expression of a by b. So, look at RSA now. Now, RSA equation is ED equivalent to 1 mod phi n. You can rewrite it in this form, but you do not know phi n. And you also do not know KD, all those things. So, in what we can do actually, you can approximate phi n by n, and that gives you this pattern. And example, if you take n of the order of, say, product of 2 primes, then the continued fraction expression looks like that, and try all the convergence. In some of the cases, you get some primes which are irrational numbers, so those are wrong answers, but you can, with proper choice of the convergence, you can get back the primes P and Q, which are these two numbers, 1, 2, 3, 4, 7 and 1, 3, 0, 0, 1. Again, I am skipping the details. Now, consider that about the primes. Say, if something is known about the primes, then what happens? So, if top half of one prime is known, then you can attack the system easily. You can get back the prime from n and top half of one of the primes. Again, similar situation for bottom half. If the contiguous data is not available, if it is known by small chunks, then 70% of one prime is needed. And for randomly known bits, no attack were known until very recent time. So, first of all, how from one half of data of a prime one can break the system? Now, you may already ask a question that why you are talking about knowing about primes? Primes are secret parameters. So, you are telling that you will be able to know half of the prime, half of the bits of the prime and all those. So, I will come to the actual attack scenario, which will show you that it may be possible to know the primes by some manner, some bits of the prime. Now, again, there are certain theorems by Coppersmith and some mathematics that I will skip, which proves using lattice-based theory, you can, if you know half of the bits of a prime, you can factorize them. Now, let us get into the randomness. Consider that some random bits of the primes P and Q are known. And then, how can we factorize n? Or how can we find out the other bits of the primes P and Q? So, what we do? We try to reconstruct the primes by finding the missing bits. So, from the LSB side, this is the scenario. If we can construct half of the bits contiguously, or from the MSB side, if we can construct half of the bits contiguously. So, this and this. Then using Coppersmith's technique, we can immediately factor. So, what is the target? Certain bits are known at the lower side, and try to fill up these gaps. How to do that? Very simple. So, though it is very simple, it came out quite late and it has been published in 2009. What they are telling that reconstruct the bits of primes starting at the LSB. What is the total search space? If you do not know anything and the primes are of length 512, then you have to try all the to the power 512 options. And in each case, it seems that there are 4 possible choices for each pair of bits of PQ, because P and Q, P can have the value 0 and 1, Q can have the value 0 and 1. So there are 4 choices. But interestingly, actually, this equation, what does that tell? If you know some bits of the primes, you can multiply them. And if you do not know, you can think of those are either 0 or 1 and multiply them. But you see that n is public. So lower side of n is known to you. So you multiply and check with the bits of n at the lower side. And that actually helps you to make it in 2 choices. So the search tree for factorization or to get certain halves of P and Q becomes actually little easier. So how many bits of P and Q do we need to know for this? So consider this notation. So I'll go through these technical details. So Pi and Qi are ith bits of PQ. So obviously P0 and Q0 are 1 because large primes. Apart from 2, all the primes are odd. And prime, odd numbers, when you write in binary form, the least significant bit is 1. So you know these are 1. And consider Pi and Qi are partial solutions for PQ through the bits 0 to I. And level I, all possibilities for Pi and Qi in the search tree. So normal branching, what will happen? 4 named choices for Pi and Qi, but that reduces to 2 because you have this relation. If you multiply this relation. So from one level, when you come to the next level, you can have at most 2 choices. Actually the choices will be less. So if either Pi or Qi is known, then the equation, this equation actually proves one path and you only have one hand in the tree. And if both are known at certain point, then either you will get one hand of the tree in the search space or the solution you have already arrived, you can tell that this cannot be a solution, so remove that option. So now consider the situation. When both the bits are known at certain point for P and Q, then either you prune the tree or the tree does not grow. If you have at least one of the bits known, then even if you do not prune the tree, you do not know the bits. You do not need to expand it. And if none of the bits are known, then you actually have both the hands of the tree. So this is the branching analysis. Suppose that alpha fraction of P bits and beta fraction of Q bits are known. So these are the situation. 2 branches, it happens with this probability. 1 branch happens with this and this probability. And in the case this will happen, you can have either 1 branch or 0 branch. So this is the total number of branches and some mathematics. So and some experimental observation. So these are certain cases. So if bits are from 1 prime are known, you need to know 50%. Bits are known in complementary fashion, you just need 25% for each of the primes, and in random positions you need only 30%. So some experiments which says that how the trees are expanded. See, for actual cases like 512 bits, there are certain cases where the size of the tree is not growing much if you know certain bits. And if there are certain bits contiguously missing, you need to apply lattice-based technique. Again, I am skipping, and we have some works in this direction. And for reconstruction of MSBs, we had certain proposals in Africa Cube where you need to know a few contiguous bits. From that you generate this part, and from this you generate this part, and this way you continue. And some experimental data. So now this is the question. So how do you know the bits of P and Q in the first place, and how do you know any RSA parameters as such? So there are a lot of side channel attacks on the computers or the cryptographic hardware. Now this is a quick summary. So the fault might not lie in the RSA algorithm, but the vulnerability may very well reside in the implementation itself. So there are several kinds of side channel attacks, timing attacks. So what you can do, so consider you are doing square and multiply. If you go for the square and multiply algorithm, if the bit is 1, then you go for square and multiply both. If the bit is 0, then you only go for square. So the number of operations in the computer are actually different. So following that, you can actually find out the bit pattern. Similar situation for power monitoring attacks. If you monitor the power that is spent in the computer, when you are doing both square and multiplication, you are spending more power. When you are doing only square, then you are spending less power. There are also radiation monitoring attacks, acoustic cryptanalysis, differential fault analysis, where you can consider a model that some adversary can actually insert a random fault in your system and try to make your system weaker. So observation, sneaking, reflection attack, and finally the cold boot attack, a new side channel attack that came up for last 3-4 years, that motivates us to study the problem. So what is cold boot attack? So by Halderman in 2008. Now most of you and the students of electronics or electrical will be knowing much better that RAMs can be thought of as an array of capacitors. So capacitors discharge slowly, not instantaneously. So RAMs retain data fragments even after you switch off your computer. So they may take several seconds to discharge, and it may take minutes or longer if you can keep it in a cold place. So that is the reason it is known as cold boot attack. So a clever attacker can boot in and read the RAM. So this is the scenario. So consider that an image is stored in a computer, and then after you switch off, with time, this is the scenario. So how can we, after the machine is switched off, so if a region decays to 0 and we get a 1, it has to be a 1 bit. If we get a 0 in that region, it may be either 0 or 1. So the rate of decay is random in various parts of the RAM. So that is the reason we have considered this problem. That is, certain bits of prime, they would be available, but certain bits won't be available. So what are the preventive measures? So storage of RSA secret keys, primes and exponents, you cannot do anything about it. If you want to use RSA, you have to store the private keys in your computer or in your handheld device. And cold boot attack. So do not leave the machine unattended. So avoid common disk encryption algorithms. Dismount encryption disk and store them securely. Control boot preferences. And in case of RSA crypto system, you may not like to use RSA crypto system, okay, but that won't happen unless you have a quantum computer, because factorization is easy in quantum model. But you can also use some lattice-based crypto system where these kinds of attacks are not there. So is this attack serious? So if you study the literature, you will find yes, indeed this attack is serious. It takes about 10 to 15 seconds to expose the RAM of a laptop. One can generate minus 50 degrees centigrade within 10 seconds using some AirStack. An external hard drive boot can beat the DRAM in 30 seconds, and at minus 50 degrees centigrade, DRAMs retain 99.9% bits up to 1 minute. So after turn on. And the attacks require little more than 50% of the complete bit. And even only for PQ, even if you consider other secret parameters of RSA, it becomes smaller. So the summary of state-of-the-art RSA cryptanalysis now is the cold boot 2009. Based on this motivation, RSA primes can be reconstructed from LSB side. 59% of the bits suffice for reconstruction if only P and Q are known. So only 27% work if P, Q, D, DP, DQ are known. And we have analyzed again carefully, and just 50% from the lower half suffice. You don't need to go through the upper half. lattice solution to find out missing bits, and completely new idea for image decide. In 2010, May has come up with again some new results, error correction of RSA prime bits. So here the model considered is that some of the bits are erroneous. You read the bits, some of the bits are correct and some of them are erroneous. Earlier, you knew that these bits are not known. Now some of the bits are erroneous and you do not know which are the bits that are erroneous. So that also gives another interesting issue. So now, what are the open problems? How to error correct cold boot data from image decide? We are working on this. Got some experimental result but couldn't solve the problem theoretically. And Q inverse mod P is an interesting thing that is stored in the structure. So what we could show, we have published a paper on this, that if Q inverse mod P is somehow completely known, then you can immediately factor it. If random parts of this thing known, then we do not know of any result yet. How about knowing some random bits from middle of P and Q? It may happen because in cold boot attack, if you try, you may get some bits from the middle. So nothing much is known here. If contiguous block is known at the middle of the primes, again we do not know. When contiguous block is known from the lower side of a prime or the higher side of a prime, then we know that. But middle part we do not know. So what can be done? LSB reconstruction, less fraction of bits if you can attack the system. MSB reconstruction, so better approximation, and then you need less number of bits, and error correction, you need to correct more bit errors. So it is a huge opportunity in this area for further research. And the lattice-based techniques are really complicated. You need to know a lot of number theory and those kinds of algorithms, LLL and all those. But for combinatorial part, constructing a binary tree, considering the width of the tree, that can be done by with BTech level or master's level background. So this is the current scenario I think I am having.